Introduction to Apache Mesos. 1. Definition of Mesos. Apache Mesos is an open-source cluster manager that provides efficient resource isolation and sharing across distributed applications or frameworks. It's a platform for resource management and scheduling in large-scale cluster environments. 2. Key features. Mesos is known for its scalability to thousands of nodes, efficient resource sharing, support for containerization technologies like Docker, and ability to run diverse workloads including Hadoop, Spark, and Kubernetes. 3. Architecture. Mesos architecture is based on a master-slave model. The Mesos master allocates resources to registered frameworks, like Hadoop or Spark, while the agents, slaves, run tasks allocated by these frameworks. 4. Use cases. Apache Mesos is used in various scenarios, including running big data frameworks, container orchestration, building private clouds, and handling resource scheduling in large-scale distributed systems. Mesos components and scheduling. 1. Mesos Master. The Mesos Master is responsible for managing the cluster resources and offering these resources to registered frameworks. 2. Mesos Agents. Agents, formerly slaves, run on each cluster node and are responsible for running tasks scheduled by the frameworks. 3. Frameworks and tasks. Frameworks are applications that run on Mesos and accept resource offers from the master. Tasks are units of work that are executed by the frameworks on the Mesos agents. 4. Resource allocation and scheduling. Mesos uses a two-level scheduling mechanism where the master offers resources to frameworks, and then each framework scheduler decides which tasks to run on those resources. Challenges and best practices in Apache Mesos. 1. Cluster configuration. Proper configuration of the Mesos cluster is crucial for optimal performance. This includes setting up the right amount of resources, network configurations, and security settings. 2. Fault tolerance and high availability. Setting up Mesos for high availability is critical. This includes running multiple master nodes and using tools like Zookeeper for leader election and state management. 3. Load balancing. Efficient load balancing across the cluster requires careful planning. Mesos offers resource offers to frameworks based on resource availability and framework demands. 4. Integrating diverse workloads. One of the key strengths of Mesos is its ability to run multiple types of workloads. Proper planning is needed to ensure different frameworks coexist without resource contention. Introduction to Apache Zookeeper. 1. Definition of Zookeeper. Apache Zookeeper is a centralized service for maintaining configuration information, naming, providing distributed synchronization, and providing group services. It's designed to be highly reliable and scalable. 2. Key features. Zookeeper's key features include high availability, fault tolerance, fast processing, simplicity of deployment, and ease of programming. 3. Architecture. Zookeeper follows a client-server model where clients can read from and write to a Zookeeper server, which manages a distributed, in-memory database to store the data. 4. Use cases. Zookeeper is used in a variety of applications, including naming services, configuration management, synchronization, leader election, and message queues. It's a critical component in distributed systems like Hadoop, Kafka, and Hbase. Core concepts of Apache Zookeeper. 1. Znodes. Znodes are the data nodes in Zookeeper's hierarchical namespace. They can store data and also have children, similar to files and directories in a file system. 2. Watchers. Watchers are a mechanism for clients to receive notifications about changes in the Zookeeper ensemble. When a watched node changes, the Zookeeper server notifies all registered clients. 3. Sessions. Client-server interactions are session-based. Each client session is assigned a unique ID, and session state is maintained by the Zookeeper ensemble. 4. Consistency guarantees. Zookeeper provides strong consistency guarantees. Updates to a singles node are atomic and linearizable, ensuring a consistent view of data. Challenges and best practices in Apache Zookeeper. 1. Ensuring high availability. Deploying Zookeeper in a replicated mode, with multiple servers, is crucial for high availability and fault tolerance. 2. Data model considerations. Designing this node structure effectively is important for maintaining an efficient Zookeeper service. 3. Security management. Implementing proper security measures, including client authentication and authorization, is essential for protecting sensitive data. 4. Performance tuning. Regular monitoring and tuning of Zookeeper's performance parameters, like tick time, max client connections, are important to ensure it operates efficiently in a distributed environment. Introduction to Apache Uzi. 1. Definition of Uzi. Apache Uzi is a workflow scheduler system to manage Apache Hadoop jobs. It is a server-based system running in a Java servlet container that schedules and executes Hadoop workloads, i.e., MapReduce, Pig, Hive jobs. 2. Key features. Uzi combines multiple jobs sequentially into one logical unit of work, offers a web-based user interface to manage and monitor the workflows, and supports several Hadoop jobs, including Java MapReduce, Streaming MapReduce, Pig, Hive, and Scoop. 3. Workflow management. Uzi workflows can define a series of jobs, each a specific Hadoop task. Workflows can be designed with decision points to control job execution paths. 4. Use cases. Uzi is used in scenarios requiring the scheduling of Hadoop jobs in a specific order, often dependent on the completion of previous jobs. It's widely used in data warehousing operations, data management tasks, and complex data processing pipelines. Uzi Workflow and Coordinator. 1. Workflow definition. An Uzi workflow is defined as an XML document, in Hadoop process definition language, that specifies the sequence of jobs to be executed. 2. Coordinator jobs. Uzi coordinator jobs are used to automate workflow execution. They can trigger workflows based on time, frequency, and data availability. 3. Action nodes. In a workflow, action nodes represent a Hadoop job or task, like a MapReduce job, Pig script, Hive query. Control nodes define job flow, start, end, and decision points. 4. Error handling. Uzi workflows include error handling for failed actions, with options to retry, skip, or fail the workflow, and notification mechanisms for job completion or failure. Challenges and best practices in Apache Uzi. 1. Complex workflow management. Designing and managing complex workflows can be challenging. It's important to plan and structure workflows for clarity and maintainability. 2. Monitoring and debugging. Effective monitoring and debugging are crucial. Uzi provides tools for logging and tracking the progress of workflows and actions. 3. Integration with Hadoop ecosystem. Uzi integrates with various components of the Hadoop ecosystem but requires careful configuration and testing for seamless operation. 4. Scalability and performance. While Uzi scales well, performance can be a concern for very large numbers of jobs. Workflow design and resource allocation should be optimized for the environment. Introduction to Apache Zeppelin. 1. Definition of Zeppelin. Apache Zeppelin is a web-based notebook that enables interactive data analytics. It allows data engineers and scientists to create, run, and share data-driven, interactive data analytics and collaborative documents with SQL, code, and visualizations. 2. Key features. Key features include support for multiple language backends, built-in data visualization, and integration with various big data processing frameworks like Apache Spark, Hadoop, and more. 3. Interactive notebooks. Zeppelin notebooks offer an interactive environment for exploring and visualizing data. They support multiple languages within a single notebook, such as Scala, Python, SQL, and more. 4. Use cases. Zeppelin is widely used for data exploration, data cleaning, numerical simulation, data visualization, machine learning, and much more in a variety of industries. Zeppelin architecture and integration. 1. Architecture overview. Zeppelin operates as a web server and interacts with a computational backend, like Spark, through interpreters. It allows users to write and execute code in various languages and display the results inline. 2. Multi-language support. Zeppelin supports multiple languages, like Scala, Python, R, SQL, in the same notebook, allowing for flexible data analysis and processing. 3. Integration with big data tools. It integrates seamlessly with various big data processing tools, including Apache Spark, Hadoop, Hive, and more, making it a versatile tool for data analysis. 4. Data visualization. Zeppelin provides built-in data visualization capabilities, including charts and graphs, to help users analyze and interpret data effectively. Challenges and best practices in Apache Zeppelin. 1. Notebook organization. Efficient organization of notebooks is vital for managing projects and workflows. Clear naming conventions and structuring are recommended. 2. Collaboration and version control. While Zeppelin supports collaboration, managing version control can be challenging. Integration with version control systems like Git is advisable. 3. Security features. Implementing security features, such as authentication and access control, is crucial, especially when working with sensitive data. 4. Performance optimization. For optimal performance, especially when working with large datasets, it's important to effectively manage resources and understand the interaction between Zeppelin and computational backends. Introduction to HU, Hadoop User Experience. 1. Definition of HU, or Hadoop User Experience, is an open-source web interface that simplifies the use of Apache Hadoop and its ecosystem components for users. It provides a user-friendly interface to interact with Hadoop clusters and its various components. 2. Key features. Key features of HU include a browser-based interface for interacting with Hadoop services, SQL editors for Hive, Impala, and other databases, job browser for MapReduce, integration with various file browsers for HDFS and S3, and dashboard for job monitoring. 3. User interface and tools. HU offers a variety of tools for data analysis, query execution, job and workflow monitoring, and file management. Its interface simplifies complex operations and makes them more accessible to a wider range of users. 4. Use cases. HU is used for data querying, browsing, management, and visualization. It's beneficial in environments where non-technical users need to interact with Hadoop ecosystem components like HDFS, MapReduce, Pig, Hive, Impala, Spark, and more. HU's integration with Hadoop ecosystem. 1. Integration with HDFS. HU provides a file browser for interacting with the Hadoop Distributed File System, HDFS. Users can browse, upload, and manage files on HDFS through a simple web interface. 2. SQL editors for databases. It includes SQL editors that allow users to write, run, and save queries for Hive, Impala, and other SQL-based languages, with syntax highlighting and autocompletion. 3. Job and workflow management. HU's job browser allows users to submit, track, and debug MapReduce jobs. It also integrates with workflow engines like Apache Uzi for scheduling and orchestration. 4. Support for multiple Hadoop services. Besides Hive and HDFS, HU integrates with other Hadoop ecosystem tools such as Apache Pig, Spark, and Solr, offering a centralized platform for various data operations. Challenges and best practices in using HU. 1. User management and security. Implementing user authentication and authorization is key for managing access in multi-user environments. HU supports integration with LDAP and Active Directory for user management. 2. Performance considerations. In large-scale deployments, ensuring HU's performance involves proper resource allocation and load balancing. 3. Customization and extension. HU can be customized to meet specific needs. Extending its capabilities to integrate with newer or custom Hadoop services may require additional development. 4. Integrating with the latest Hadoop components. Keeping HU compatible with the latest versions of Hadoop components can be challenging. Regular updates and testing are required to ensure smooth integration. Introduction to Apache Spark. 1. Definition of Spark. Apache Spark is an open-source, distributed computing system that offers an interface for programming entire clusters with implicit data parallelism and fault tolerance. Originally developed at UC Berkeley's AMPLab, it has become one of the key big data distributed processing frameworks. 2. Key features. Spark's main features include speed, capable of running programs up to 100x faster than Hadoop MapReduce, ease of use, supports applications written in Java, Scala, Python, and R, and a rich set of higher-level tools including Spark SQL, mlib for machine learning, graphics, and Spark streaming. 3. Spark components. The core Spark API allows data parallelism and fault tolerance on clusters. Spark SQL provides a new data frame API and SQL support. mlib is a library of machine learning algorithms. Graphics is for graph processing, and Spark streaming enables scalable, high-throughput, fault-tolerant stream processing. 4. Use cases. Spark is used for a wide range of applications, including real-time data processing, machine learning and predictive analytics, data integration, and ETL processes. Spark architecture and data processing. 1. Distributed processing. Spark's distributed processing capability is designed to handle large-scale data analytics. It distributes data and computation across clusters, enabling parallel processing. 2. Resilient distributed datasets, RDDs. RDDs are the fundamental data structure of Spark. They are immutable, distributed collections of objects, which can be created and manipulated through transformations and actions. 3. Data frames and datasets. Data frames are a distributed collection of data organized into named columns, similar to a table in a relational database. Datasets are a type-safe version of data frames, available in Scala and Java. 4. Cluster managers. Spark supports several cluster managers including its own standalone cluster manager, Hadoop Yarn, and Apache Mesos. Challenges and best practices in Apache Spark. 1. Memory management. Efficient memory management is key to optimizing Spark's performance. It involves understanding the memory usage patterns and tuning the Spark configurations accordingly. 2. Performance optimization. Performance tuning in Spark often involves optimizing data partitioning, caching datasets, and selecting the right transformations and actions. 3. Data serialization. Efficient serialization can significantly impact Spark's performance, especially for network-intensive applications. Choosing the right serialization format is crucial. 4. Fault tolerance and reliability. Spark's built-in fault tolerance mechanisms, such as RDD lineage, need to be well understood and leveraged to ensure data processing reliability. Introduction to Apache Flink. 1. Real-time stream processing framework. Apache Flink is a powerful, open-source stream processing framework for real-time and large-scale data processing tasks. 2. Key features. It offers high throughput and low latency, fault tolerance, stateful computations, and event time processing. 3. Architecture. Flink's architecture is distributed and scalable, supporting consistent stateful computations and customizable memory management. 4. Use cases. Commonly used for real-time analytics, complex event processing, and data pipeline applications, including fraud detection and monitoring systems. Architecture of Apache Flink. 1. Distributed processing engine. Flink operates in a cluster environment with a master-slave architecture. It is designed to run on various cluster managers like Yarn, Kubernetes, or standalone. 2. Task Manager and Job Manager. The Job Manager is the master node responsible for job scheduling and resource management, while task managers are worker nodes executing tasks. 3. Data Stream API and Dataset API. Flink provides two core APIs, the Data Stream API for stream processing and the Dataset API for batch processing, enabling versatile data processing capabilities. 4. State management. Flink offers advanced state management, allowing for fault-tolerant stateful computations and ensuring data consistency across distributed environments. Challenges of Apache Flink. 1. State management. Managing state consistently across distributed systems poses a significant challenge, especially for exactly once processing semantics. 2. Fault tolerance. Implementing effective fault tolerance mechanisms to handle node failures while maintaining processing accuracy. 3. Stream processing at scale. Scaling the system to handle high throughput, low latency streaming data while balancing resource usage. 4. Complex event processing. Dealing with complex event patterns and timely processing of streaming data in real-world scenarios. Best practices in Apache Flink. 1. Efficient resource utilization. Optimize resource allocation, CPU, memory, for Flink tasks to enhance performance and reduce costs. 2. Effective state management. Leverage Flink state management features, like stateful computations and checkpoints, for consistent data processing. 3. Scalability planning. Plan the scalability of Flink applications, considering factors like parallelism, task slots, and network buffers. 4. Continuous monitoring. Implement continuous monitoring and tuning of Flink applications to identify bottlenecks and optimize performance. Introduction to Apache Storm. 1. Real-time computation system. Apache Storm is a distributed real-time computation system for processing large volumes of high-velocity data. 2. Open source and scalable. It is open source and designed to be highly scalable, capable of handling massive data streams across a cluster of computers. 3. Stream processing. Storm provides a framework for stream processing and real-time analytics, allowing for the transformation and aggregation of streaming data. 4. Use cases. Ideal for scenarios requiring real-time analytics, online machine learning, continuous computation, distributed RPC, ETL, and more. Architecture of Apache Storm. 1. Topology structure. A Storm cluster runs topologies, which are network graphs defining the data flow and processing logic. 2. Spouts and bolts. Topologies consist of spouts, data sources, and bolts, data processing units, which process incoming data streams. 3. Nimbus and supervisor nodes. The Nimbus node distributes code, assigns tasks, and monitors failures. Supervisor nodes execute tasks assigned by Nimbus on worker processes. 4. Stream groupings defines how data is passed from one component to another, with different grouping strategies like shuffle, fields, all, direct, and global. Challenges of Apache Storm. 1. Complex event processing. Managing and processing complex event patterns in real time can be challenging. 2. Fault tolerance. Ensuring the system's reliability and fault tolerance during node failures or network issues. 3. Managing state. Handling stateful computations and ensuring consistency across distributed nodes. 4. Scalability and performance. Scaling the system effectively to handle high throughput while maintaining low latency and system performance. Best practices in Apache Storm. 1. Topology design. Design topologies with efficient data flow and processing logic. Optimize spout and bolt configurations for better performance. 2. Resource allocation. Appropriately allocate resources such as CPU, memory, and network bandwidth for optimal performance. 3. State management. Use state management techniques effectively to ensure data consistency and reliability. 4. Monitoring and tuning. Continuously monitor the system's performance and tune configurations to handle varying workloads and optimize throughput. Introduction to Apache NiFi. 1. Dataflow automation. Apache NiFi is a powerful, user-friendly tool for automating and managing the flow of data between systems. 2. User-friendly design. Features an intuitive web-based interface for designing, controlling, and monitoring data flows. 3. Supports various data formats, capable of processing and distributing data in various formats, making it versatile for different integration scenarios. 4. Real-time data processing. Designed for real-time data processing and streaming, providing rapid insights and responses. Architecture of Apache NiFi. 1. Components. Consists of processors, connections, flow controllers, and data repositories for robust data flow management. 2. Data provenance. Tracks data from origin to destination, ensuring transparency and traceability. 3. Extensible design. Allows for custom processors and integration with other systems, enhancing its adaptability. 4. Secure data flow. Implements robust security features for safe data transfer and access control. Challenges in Apache NiFi. 1. Complex configuration. Setting up and configuring NiFi for specific use cases can be complex and time-consuming. 2. Scalability issues. Scaling NiFi for high volume and high velocity data can be challenging. 3. Monitoring large data flows. Effectively monitoring and managing large data flows requires significant oversight. 4. Security management. Implementing and maintaining robust security measures is essential but can be complex. Best practices in Apache NiFi. 1. Incremental deployment. Start small and scale gradually to understand NiFi's capabilities and limitations. 2. Data flow management. Regularly review and optimize data flows for efficiency and performance. 3. Regular backups. Maintain regular backups of NiFi configurations and metadata for recovery purposes. 4. Continuous monitoring. Implement continuous monitoring strategies for early detection of issues and performance bottlenecks. Introduction to Apache Druid. 1. High-performance analytics. Apache Druid is an open-source analytics database designed for fast aggregations and queries on large volumes of event data. 2. Real-time data ingestion. Capable of ingesting data in real time, enabling immediate data analysis and decision-making. 3. Scalable architecture. Built to scale horizontally, handling large data volumes efficiently across multiple nodes. 4. Multi-tenant capabilities. Supports multi-tenancy, making it suitable for environments with multiple users or applications. Architecture of Apache Druid. 1. Distributed components. Consists of various distributed components like brokers, historical nodes, coordinators, and ingestion nodes. 2. Columnar storage format. Utilizes a columnar storage format for fast querying and data compression. 3. Data segmentation. Stores data in segments, optimizing for both real-time and historical data analysis. 4. Query layer. Features a flexible query layer capable of handling a wide range of analytic queries with low latency. Challenges in Apache Druid. 1. Complex setup. Setting up and configuring Druid can be complex, requiring a good understanding of its architecture. 2. Resource intensive. high-performance capabilities come with significant resource requirements, especially for larger deployments. 3. Data management. Efficiently managing and indexing large volumes of data can be challenging. 4. Query optimization. Optimizing queries for best performance requires deep understanding of Druid's query engine. Best practices in Apache Druid. 1. Incremental scaling. Start with a smaller deployment and scale as needed to understand performance impacts. 2. Query tuning. Regularly tune and optimize queries for efficiency and to reduce resource consumption. 3. Monitoring and alerting. Implement monitoring for cluster health and performance, with alerting for potential issues. 4. Data retention policies. Establish data retention policies to manage storage efficiently and keep data sizes in check. Introduction to Apache Beam. 1. Unified Programming Model. Apache Beam provides a unified programming model for batch and streaming data processing. 2. Multi-language support. Supports multiple languages including Java, Python, and Go, allowing developers to use their preferred language. 3. Portable pipeline execution. Beam pipelines can be executed on various execution engines like Apache Flink, Apache Spark, and Google Cloud Dataflow. 4. Diverse data sources, capable of handling data from various sources and formats, offering flexibility in data integration. Architecture of Apache Beam. 1. Abstract Pipeline Model. Utilizes an abstraction layer for defining data processing pipelines, independent of the underlying execution engine. 2. Runners. Provides runners for different processing engines, enabling the same pipeline to run on multiple execution environments. 3. SDKs. Offers software development kits for developing pipelines in different programming languages. 4. I/O connectors. Includes a variety of I/O connectors for reading from and writing to different data sources and sinks. Challenges in Apache Beam. 1. Complex pipeline design. Designing efficient and robust Beam pipelines can be complex, especially for large-scale data processing. 2. Performance tuning. Tuning performance across different runners and execution environments can be challenging. 3. Multi-platform execution. Ensuring consistent behavior and performance across different execution platforms requires thorough testing. 4. Debugging and monitoring. Debugging and monitoring pipelines, especially in distributed environments, can be difficult. Best practices in Apache Beam. 1. Modular pipeline design. Design pipelines in a modular way to simplify development, testing, and maintenance. 2. Runner-specific optimizations. Optimize pipelines for specific runners where necessary to achieve better performance. 3. Thorough testing. Test pipelines thoroughly across different runners and data sources to ensure reliability and correctness. 4. Efficient resource usage. Monitor resource usage and optimize to ensure efficient processing, especially in large-scale deployments. Thanks for watching.